The mineral fillers less commonly used in plastics are halloysite, nanoclay, silica in the form of quartz, novaculite, or cristobalite, Nepheline Syenite, and diatomite. Halloysite is a clay mineral with a hollow tubular form. It is naturally exfoliated, so the tubes readily separate and disperse. Wetting through the tubes can provide mechanical bonding for effective reinforcement even without coupling agents or surface modifications. Nanoneedles plus high aspect ratio can offer a favorable balance of reinforcement and impact improvement. The very fine particle size promotes nucleation. Nanoclay, also known as organoclay in other industries, is made by reacting an aqueous dispersion of montmorillonite with a cationic surfactant, for example, a fatty quaternary ammonium compound. The surfactant replaces the alkali or alkaline earth cation that naturally neutralizes the anionic charge of the clay lattice, making the clay hydrophobic and oleophilic. The resulting nanoclay is filtered and dried. The coating on the clay facilitates the lamination so that the platy clay crystals can disperse in a polymer matrix and provide reinforcement and barrier properties at low loadings, typically less than 5%, and with minimal impact on compound density. Ground silica, also known as ground quartz or silica flour, is produced by grinding high-purity quartz to finer than 200 mesh. Air separation is used as required to remove mineral impurities. Ground silica for filler uses offers high brightness, low moisture, chemical inertness, relatively low surface area, and the low liquid absorption that allows high loading levels. Novaculite is microcrystalline quartz that is milled to low moisture, high purity platy particles. Brightness is generally lower than for other forms of ground silica, but novaculite offers higher aspect ratio, lower binder demand, lower abrasivity, and availability in a range of particle size distributions to as small as 2 micrometers average. Film-grade cristobalite is produced by the high-temperature conversion of high-purity quartz. Its low index of refraction makes it particularly suitable as an anti-block in clear polyolefin films. It promotes heat retention in thermal horticultural films, and its low oil absorption allows for high loadings, greater than 50% by weight, in these applications. In North America, Nepheline Syenite consists of approximately 25% nepheline, 55% sodium feldspar, and 20% potassium feldspar. Nepheline has the same aluminum silicate structure as feldspar, except for a higher substitution of aluminum for silicon in the silicate lattice. The basic filler properties of feldspar and Nepheline Syenite are similar: low vehicle demand and improvement of a compound's resistance to abrasion and chemical degradation. Feldspar is generally preferred in applications where a very fine particle size is not required, but hardness and inertness is, for example, pipe for abrasive and acidic slurries. Nepheline Syenite is preferred for its higher brightness and a broader range of fine grinds, 325 mesh to 1250 mesh. Both feldspar and Nepheline Syenite have a low refractive index that makes them suitable as an anti-block in polyolefin films. However, Nepheline Syenite is more readily available in the controlled particle size distributions required for minimal film haze and for thermal horticultural films. Diatomite products are generally differentiated by process and particle size. Flux calcined diatomite is calcined at about 1200 degrees C with sodium carbonate or sodium chloride. The flux converts iron oxides to a colorless glassy phase, resulting in a white product. Flux calcined diatomite is milled, screened, and air classified, with coarse fractions sold for filtration uses and fine fractions as white fillers. These products provide maximum void volume, which can exceed 90%, and consequent high absorptivity. Straight calcined diatomite is heated to between 870 and 1100 degrees C. Calcination at these temperatures generally turns the diatomite pink from iron oxidation, so it is used primarily for filtration applications and seldom as a filler. Natural diatomite products are gently crushed and milled to retain the frustule shape, and then screened and air classified to remove impurities and to segregate products into coarse fractions for filtration applications and fine fractions for filler uses. The primary application for diatomite in plastics is as an antiblock in polyolefin films.